In this video, we'll do a direct calculation of thermal expansion. We're dealing with an aluminum bar. It has a length of 1.000, etc. meters, and the temperature right now is 68 degrees Fahrenheit. We want to calculate the length when the temperature becomes 100 degrees Fahrenheit. So thermal expansion occurs as the particles, the molecules inside the material, vibrate more and take up more space. I won't go into that detail, but there is a direct approximate calculation for the expansion. The increase in the length, delta L, is equal to a coefficient that depends on the material. So there'll be a certain number here we'll use for aluminum. The original length, L sub naught, is the original length. We're going to put in 1 meter for that. And then the change in the temperatures. So we have a T naught, an original temperature, and most tables that you would refer to for this, T naught will be 20 degrees Celsius. And both of these T numbers do need to be in Celsius for most tables that you would look up the alpha value for. So that's for one of our first tasks. We need to change these temperatures in Fahrenheit to Celsius. So I've retrieved the value of alpha, the thermal expansion coefficient for aluminum, 22 times 10 to the minus 6, 1 over degrees Celsius. 1 over degrees Celsius. I might just make a brief comment about this. The delta L is going to be in meters. L naught is in meters. The units of alpha, 1 over degrees Celsius, and the units in the parentheses here will be degrees Celsius. So degrees Celsius units cancel. So how do we find degrees Celsius if we're given Fahrenheit? First subtract 32 from the Fahrenheit number and then multiply by 5/9. So doing that for 68 degrees Fahrenheit gives us this 20 degree Celsius number. That's the reason I chose 68 degrees Fahrenheit. So I knew I was going to come up with 20. And then the 100 degrees Fahrenheit changes to 37.8 degrees Celsius. So to do the delta L, we have the information we need. Alpha, L naught, T minus T naught. So the alpha number, the original length, and then 37.8 minus 20 gives us our temperature change of 17.8. And the delta L, and again, you should pause and do this calculation yourself. First, do the subtraction here, 37.8 minus 20, then times 1 meter, then times 22 times 10 to the minus 6. And we find the change in the length is 3.92 times 10 to the minus 4 meters, 0.000392. Is this the length of the aluminum rod? No, this is how much it's changed. This is the delta L. To find the length, we have to add on the original length of 1 meter and the increase in length, 0.000392 meters. So this will be the new length of our aluminum rod. So there's a straightforward calculation of thermal expansion, linear expansion. There are other formulas for volume expansion. This is linear expansion. You need to find a table that has the alpha for the material you're dealing with. You need to know the original length. You need to know the change in the temperatures, and then you can calculate delta L. And of course, there may be variations of this problem. You may be given delta L, and you're asked to find the original length, or you're asked to find one of the temperatures here. Various combinations of problems can be generated using this thermal expansion calculation. So if you want to see some more videos on physics topics, go to physics.gpclements.com. It's free, no registration. You'll find a list of the videos and a brief description about them, how long they are. Or astronomy videos, astronomy.gpclements.com, and the astronomy site also has the current sky calendar, a list of some of the events that are happening for the current year. And if you like these videos, please subscribe to my YouTube channel.